Bismillahirrahmanirrahim. I am Dr. Javed Ali, Assistant Professor, Department of Chemistry, Cust. Welcome to the course Physical Chemistry 2. Course code is 332. Today's topic is kinetics of zero order reaction. Outline of the topic: Introduction to rate law and order of reaction. Kinetics of zero order reaction, mathematical equation and data interpretation. Before discussing zero order kinetics, first of all, what is rate law of reaction? The rate of a reaction is a function of reactant concentrations. This functional relation between the rate of reaction and the concentration of reaction is called the rate law, which can be represented by this equation. Minus dA divided by dt is equal to Ka, where A is concentration of reactant, K is rate constant. Minus dA divided by dt represents decrease in concentration of reactant. So this equation is known as rate law or rate expression. A rate constant is a proportionality constant that appears in the rate law. For example, the K is the rate constant in this rate expression or rate law. So this K is known as rate constant. Order of reaction. Now what is order of reaction? The sum of the powers of concentration terms in the rate equation is known as order of reaction. Consider a chemical reaction. A plus B is giving you product, where A represents one reactant and B represents another reactant, while M is the number of moles of reactant A and N represent the number of moles of reactant B. So the rate law is rate is equal to K A power M B power N. So M represents the concentration of reactant A and N represent the concentration of reactant B. And order of reaction with respect to A is M and order of reaction with respect to B is N. And overall order of this reaction is M plus N, as we already mentioned that the sum of the powers of concentration term. So this is known as order of reaction. Most important types of reaction orders are zero order, first order, second order and third order. However, fraction order of reaction is also possible. First of all, we will discuss these important orders for reaction, and later on we will discuss the fraction order in this course as well. So first of all, what is zero order reaction? The rate law for zero order reaction is dP divided by dt is equal to Ka power 0, or minus dA divided by dt is equal to Ka power 0, where A represents the concentration of reactant, K represents the rate constant, and dP divided by dt represents the rate of formation of product. P represents concentration of product, while A represents the concentration of reactant. So this equation represents rate of formation of product is equal to Ka power 0. And this equation represents the rate of decrease in reactant concentration is equal to Ka power naught. So the rate of reaction is independent of the reactant concentration. The rate of formation of product will not depend on the concentration of reactant. Similarly, the rate of disappearance of reactant is not dependent on reactant according to this equation, because the power is 0 and anything power 0 is equal to 1. So the rate of formation of product or rate of disappearance of reactant is independent of reactant or reactant's concentration. So this is differential equation for zero order reaction. Minus dA divided by dt is equal to Ka power naught, where A is concentration of reactant, T is time, while K is rate constant. So we can simplify this equation because we know A power naught is equal to 1, and we can shift dt to another side. So now the equation is minus dA is equal to K dt, and A power naught is equal to 1. To convert this equation into integrated form, we can take integration of this equation. Now K is constant, so we can take out K from integration. So now the equation is minus integration dA is equal to K integration dt. We know integration of dA is equal to A, and similarly integration of dt is equal to T. So the equation is now minus concentration of reactant A is equal to Kt plus Z. Z represent integration constant here. Where Z is integration constant. The value of Z can be determined by putting the value of A is equal to A naught at T0. When we put the T value is 0, so that Kt becomes 0. And A value is A naught. So we get the Z value, which is minus A naught. By putting the Z value in the zero order equation, we get this equation. Minus A is equal to Kt minus A naught. By rearranging this equation, we get A naught minus A is equal to Kt. Or Kt is equal to A naught minus A. This is integrated form of zero order reaction. Because we know A naught minus A is equal to X, X represents the concentration of product. A naught represents the initial concentration of reactant, A represents the concentration of reactant at any T. So A naught minus A represents the concentration of product. So Kt is equal to X. These two are very important equation for zero order kinetics. These equation represents that the rate of formation of products only depend upon K and time, and not depend on concentration of reactant. So when K value is high, the rate of formation or the concentration of product will high, and the more time given to reaction, the rate of formation or concentration of product will high. The integrated equation for zero order reaction is Kt is equal to A naught minus A, and A naught minus A is also equal to X. X represents the concentration of product. The product formation is independent of reactant concentration and only depend on time and rate constant. Zero order reaction graph. We can plot the concentration of reactant versus T. The concentration of reactant will decrease with respect to time with constant slope. It means the rate of disappearance of reactant with respect to time is constant, and it is independent of reactant concentration. Similarly, the rate of formation of product with respect to time will give you a straight line with constant positive slope. So if we plot the reactant concentration with respect to time and get a straight line with negative slope, this represents that this reaction is following zero order kinetics. We can also determine the rate of reaction by plotting a rate of reaction versus concentration. As we know, the rate of reaction is independent of reactant concentration, so we will get a straight line with zero slope. The zero slope represents that there is no change in rate of reaction with respect to concentration. So we can determine the rate of zero order reaction by plotting reactant concentration versus T, or by plotting rate of reaction versus reactant concentration. Half-life of zero order reaction. Half-life is defined as the time required for reducing the concentration to half of its original value. We know the integrated equation of zero order kinetics, which is Kt is equal to A naught minus T. So to determine the half-life for zero order kinetics, we can put A value is equal to 0.5 A naught, because the half-life can define as the time required for reducing concentration to half of its value. So we can put 0.5 A naught instead of A. And similarly, we can represent T with T half. T half is half-life. So by subtracting 0.5 A naught from A, we get 0.5 A naught. So now the equation is K T half is equal to 0.5 A. We can also write this equation as K T half is equal to A naught divided by 2, as 0.5 is also equal to 1 divided by 2. By further rearranging, half-life is equal to A naught divided by 2K. So the half-life is proportional to the initial concentration of reactant. In this equation, 2 is constant, K is constant, and the half-life is directly proportional to the initial concentration of reactant. When initial concentration of reactant is high, then the half-life will high. And similarly, when initial concentration of reactant is smaller, then the half-life will smaller. With help of this equation, we can calculate the half-life of reaction if we know the rate constant, and similarly we can calculate the rate constant if we know the half-life and initial concentration. For example, if K value is 0.1 moles per liter per second and initial concentration is 2 moles per liter, then we can calculate the half-life for the reaction. As we know that half-life is equal to A naught divided by 2K. We get half-life is equal to 2 moles per liter divided by 2 into 0.1 moles per liter per second, where 2 moles per liter is value of A naught and 0.1 moles per liter per second is value of K. So the half-life for this reaction is 10 seconds. Similarly, when the A naught value is 1 moles per liter and K is 0.1 moles per liter per second, by putting the value of A naught and K in half-life equation, we get half-life is equal to 1 moles per liter divided by 2 into 0.1 moles per liter per second. Moles per liter and moles per liter will cancel with each other, and 1 divided by 2 into 0.1 is equal to 5. So the half-life for this reaction is 5 seconds. When the A naught value was 2, the half-life was 10 seconds. When A naught is 1, the half-life also reduced to 5 seconds. This is because the half-life is directly proportional to A naught. Example of zero-order kinetics. Decomposition of ammonia to nitrogen and hydrogen is example of zero-order kinetics. It doesn't depend on ammonia concentration, but it's only depend on rate constant and time. Similarly, decomposition of hydrogen iodide to hydrogen and iodine gases are also example of zero-order kinetics. Summary of today's topic. Rate of the reaction is independent of the reactant concentration. The rate constant unit is concentration per time. If we represent the concentration in moles per decimeter cube, then the rate constant unit will moles per decimeter cube per second. And similarly, if we represent the concentration in moles per liter, then the rate constant unit will become moles per liter per second. The integrated equation for zero-order reaction. Kt is equal to A naught minus A, where A naught represents the initial concentration of reactant and A represents the concentration of reactant at any time. K represents the rate constant and T represents the reaction time. Similarly, we can also represent the integrated equation for zero-order kinetics as Kt is equal to X. X represents the concentration of product. As we know, A naught minus A is equal to X. These two are very important equations, and we can predict and determine the concentration of product at any T if we know the rate constant. Just by putting the value of T, we can determine the concentration of product. Similarly, if we know the initial concentration and the rate constant, we can determine the reactant concentration at any time. Furthermore, if we know the initial concentration of reactant and the reactant concentration at any T, we can determine the rate constant. So these two are very important equation. With the help of these equation, we can determine the reactant concentration at any T. We can also calculate the time required for a particular product or reactant concentration. The half-life of reaction is proportional to initial concentration of the reactant. These are some references for today's topic. At the end, thank you very much.